All right, everybody, welcome to Calculus 2. So we have our first exam this Friday. It's going to be from 8 to 10 p.m. and it's going to be proctored via HonorLock. So make sure you guys are using Google Chrome and make sure you have HonorLock installed prior to the exam. If this is your first time using HonorLock, or this is maybe the first exam this semester you're using HonorLock for, I'm going to put up a little like practice HonorLock quiz. So you can kind of just get used to using it. It'll like take you through the proctoring intro where you have to like scan your room and show your scratch paper and stuff like that. And then you just answer like 2 yes or no questions or something, and that's it. So it kind of just gets you used to the setup. So I recommend taking that if you would want some practice with that. Other announcements, this evening from 6 to 8 p.m., we are going to, the Teaching Center is going to have a review session for this exam. So Teaching Center, 6 to 8 p.m. And I will provide a Zoom link in an announcement. So after class, I'll send out an announcement with the Zoom link for this. Right.
Oh, what day is that?
Today.
Yeah, will there be a recording?
Yeah, I was about to say that. Yeah, so if you guys can't make it, then don't worry. They're going to post a recording. They'll send me a link to recording, and then I'll give that to you guys. All right, let's see. What other announcements do we have here? So for class on Friday, essentially class on Friday is just going to be office hours. So I'm here to answer any questions that you guys have, but there's not really going to be any class structure or anything like that. It's just you guys asking questions. That's not too dissimilar from what we're going to do today. I want you guys to maybe bring any questions that you guys have on any topics or materials, and we'll be doing those today. So I'm happy to answer any questions you have. In particular, I'm happy to answer any questions on the practice exam or on maybe on homework 8 or something like that. So although I recommend saving homework 8 maybe for discussion section, and then we can do the practice exam in here. But it's whatever you guys want to do. I'm not putting any formal limits on it or anything. All right, so the way this is going to work, the way I did this kind of review in my other class is there are 189 people online, and there are like less than 20 people in here. So it's not fair if I kind of alternate between an in-person person and an online person. What I'm going to do is I'm going to answer 3 questions from the chat, and then I'm going to answer 1 question live. I want to make sure the live people get at least a chance to answer 1 or 2 questions, but I know that disproportionately this class is made up of online people. So I'm going to mostly take questions from the Zoom chat here. Now let's see here. The way I'm going to do this is I'm going to do it by popularity. I tried to do it by order before, but then I end up like trying to scroll through the chat to find out where I last was, and that's really inefficient. So I'm going to take the next minute or so. I want you guys in the chat to put in whatever question you want. And I ask that you only type it in once. So don't like just spam it over and over and over and over again. Just type it in once, and then I'll see which ones the most popular are. So why don't you go ahead and do that now? I have a lot of different questions here. I think I'm starting to see some bias towards volume of revolution. Oh, by the way, yeah, so before class, someone asked me about homework 8, number 1. So if you're interested in that problem, the complete solution is right there. Okay.
I asked like a quick question. So when after like the homework like closes, we aren't really able to access the Chronos page anymore to look at those questions.
If you go to the assignments tab and you go to old homework, any assignment that's been previously due, there's a copy of it there that you can just mess around with and do as much as you want.
Where is it? So it's on assignments, past assignments.
Yeah, go to click on the assignments tab on the left part of Canvas, and then go down to old homework / non-grade assignments. It's the same place where the practice exam is.
Oh, so I see. Oh, yeah, I see the copies. Never mind.
Oh, you do? Oh,
No, I said I do see the copies.
well, no, someone said they get a 500 error when they try to access those. Let me look into that. Hopefully, people have successfully done them, so I'm not sure what it is. Okay.
I have a quick question about the exam. Did you say it was out of 100?
Yeah, there's 105 possible points, and it'll be scored out of 100.
All right, I was just wondering because the grade book shows it as out of 105.
Yeah, that'll be amended.
Oh, okay.
How many
Thank you.
questions is the exam?
It's gonna be 17 questions, 5 points each. All right, I think homework 8, number 10 is the winner here. All right, so let's take a look at that. Okay. Oh, this one, yeah, this one's a bit tricky. This is probably like one of the harder force ones. Okay, so a swimming pool of width 8 meters and a length of 10 meters extends linearly. Oh, starts. Wait, no, yeah. Wait, that was okay. A length of 10 meters starts at a depth of 0 meters and extends linearly downward to a depth of 5 meters. Okay. So find the force due to pressure on the bottom of the pool. Okay. And they give you a warning here. The thickness of each slice is not just going to be DH. We're kind of accustomed to that. In every problem, whenever we have some tiny little thing, it's going to be of length DH. This will be an exception. It'll actually be slightly different. So as with all these problems, let's draw a picture. All right, so we know that the pool is 8 meters wide. It starts at a depth of 0 and then it extends downward to a depth of 5. So it looks something like this. All right. So this length right here is 10, and then this length right here is 5. So it takes 10 meters for us to get down to a depth of 5 meters right here. And what we want to know is we want to know the force due to pressure on the bottom of the pool, which is slanted. All right, so what I'm going to do is I'm going to do the same thing I always do. I'm going to have my y be 0, and then I'm going to have it increase downwards here. Now, what I'm going to do is I'm going to take a little slice across the edge of the pool here, and I'm going to try to figure out the amount of force due to pressure on that slice right here. All right, so let's see here. So we're looking at the force on one slice. That's going to be rho G. Oh, I guess I'll call this H. I usually call this H. Rho G H A. Okay, now this time the area of this rectangle, the easy part's going to be the width and the hard part is going to be the height. So what's the width of this rectangle, no matter where we are? It's 8, right? It's going to be 8 across. So this has a width of 8. But then we need to know the length of this. And it's tempting to just put DH, like, oh, it's a tiny little change this way. But DH is a tiny little change up and down perfectly vertically. It's not necessarily a tiny little change diagonally here. So what we're going to do is I'm going to kind of zoom in on this right here. So I'm going to kind of zoom in. What we have here is we have a triangle that looks like this, where we have DH here, and we really want to know what the length is up here. All right, now it takes it 10 meters to go down 5, right? So the proportions of this triangle are going to be 5 DH and then 10 DH. Although we could simplify this to be DH and then 2 DH. So now we want to get what the hypotenuse of this is. Why is it a triangle? Because we're going down a slope here. We can imagine this is like the side view of our slope right here. So that's why it's a triangle right here. All right. So now we want to know what this is. Well, we use the Pythagorean theorem to get that. We have DH squared plus 4 DH squared is, I guess I'll call this maybe X. All right. So then I add this together, I have 5 DH squared, and then I take a square root. So this isn't just going to be DH, this is going to be square root of 5 DH. Right here. So that's what I'm going to put in here. So I have rho GH 8 root 5 DH. So that's what's going on here. So is the slice a triangular prism? Well, the slice is a 2D shape, right? Like I'm still looking at this as a rectangle. I just need to know what the tiny little length of this rectangle is. And the rectangle is lying on this ramp. So I need to know about the proportions of this ramp in order to tell me how long the rectangle is here. We're still just looking at slices of rectangles. We're always going to use rectangles for these force problems here. There's actually another way to do the problem. We could have also made H go down at an angle, but that would have had its own set of issues. So that wouldn't have necessarily been any easier to do it that way. All right. So now we have root 5 DH, and then all we need to do now is throw this into an integral. Okay, so we have 8 root 5 rho GH DH. Now let's see here. What are the bounds of this integral going to be? Where is the ramp in terms of H? What's the lowest H value we're going to have the ramp at? Oh, sorry. Yeah, I guess I confused lowest and deepest. Yeah, so this ramp goes down to a depth of 5, and it starts all the way up here at a depth of 0. So this is going to be the integral from 0 to 5 of all of this stuff. And to save time, now that we've gotten here, this is just the integral of H dH. It'll just turn into H squared over 2, and then you plug in your number. So I want to make sure we have time for other questions here. So I'll just leave it like this, and then now you guys can do it. This integral isn't going to be too bad here. All right, another question I saw on the chat a little while ago was talking about volumes of revolution. And a lot of people were wondering, which technique do I use in which situation? So I want to talk about that. I think that's something on a lot of people's mind. Keep this happen here. All right. So remember, for volumes of revolution, there's a really nice chart that will let you know which method to use in which instance. So we have the axis, and then we have function of. All right, well, I don't need the rest of that. Or this. Okay, so let's say we have functions of x. Like let's say we have f of x. Like for an example, we have like y equals x squared and y equals x or something like that. And then we either could spin around the x-axis or the y-axis. All right. So with the x-axis right here, and we have a function of x, what are we going to do here? We're going to use the washer method, which is pi, and then we have the integral of f of x squared minus g of x squared. So it's going to be the washer method if the variable and the axis match up. Now, if they're different, if we have functions of x and it's around the y-axis right here, then we're going to have 2 pi times the integral from a to b of x times f of x minus g of x. All right, and this is the shell method. Okay, now let's say we have functions of y. So let's say we have maybe like x is sine of y, x is e to the y, or something like that. All right, so then what are we going to do here? For this one, we're going to use the shell method if we're spinning around x. So it's 2 pi a to b y, f of y minus g of y. And then for washer, we're going to do that when we have f of y around the y-axis right here. All right. Now, I think someone asked about the bounds. The bounds are always going to be whatever these are. So if you have an integral with respect to x, then the things you should put in for your bounds are x values. The lowest x value where you have your shape and the highest x value where you have your shape. And then the same thing goes with y. If you have y as your integral right here, then your lower bound is going to be a y value. Your upper bound is going to be your y value. And how do I know which one do I put first? Well, one kind of dumb way to know which one you put first is whichever one makes the answer positive. Because remember, we're measuring volumes here, so we should always get a positive answer. The more kind of, I guess, correct way of doing it is whichever one is further from the axis is going to be your f of x, and whichever one is closer to the axis you're spinning around should be your g. That's how you figure it out in that case right here. Does that mean I have to draw it out? I strongly suggest that you draw out anything involving volumes of revolution or computing volumes with cross section or doing any of the physics problems. I recommend you draw any and all of those out. All right. So let's see here. So I answered this question. Why don't I take one more from the chat here? If we get a negative answer, can we switch the sign? There's a good chance that you could just do that and get the correct answer. Not guaranteeing it, but there's a good chance. All right, let's see. Seven from the practice exam. Homework 8, number 4. 7. Remember, no cheating, no saying it more than once. If you like, no saying it more than once for one person. Am I still having office hours tomorrow? Yeah. Office hours are periods 4 and 5. Why was it 2H on the bottom? Well, the proportions of 5 and 10 simplify the proportions of 1 and 2. That's what's going on there. Seems like we have an epic battle between doing homework 7, number 7, and practice exam number 7. We'll see who's going to win. You guys, another 30 seconds. Oh boy. Yeah, we're definitely gonna do number 7. Oh my God. Okay, why don't we do the practice exam, number 7? Well, I used to do it where like I took it in the order that I got them in the chat, but then I had to scroll through like hundreds of messages going back up to the top to see what's going on. Okay, this is another physics problem, so I'm glad someone asked about this. How about, all right, so what's going to happen is I'll do this number 7, the practice exam 7. And then I'll take a question from the audience here, because then we'll have 3 from the chat. And then I'll go do homework number 7 after the audience question. All right, so practice exam 7, a tank in the shape of a pyramid of height 3 and base side length 1 is filled to a height of 1 with water. All right, how much work to pump out the water? All right, let's see here. So let's draw a picture. As I always say, we should draw a picture for these. So here is our base of length 1, and then we have a height of 3. So it kind of looks like a metronome or a prism, I guess. We have 1, 1, and then we have a height of 3. Now the water is filled to a height of 1. So it's filled up this much with water right here. So we need to know how much work it's going to take for all this water to kind of pop out at the top. All right, so let's see here. So let's take one slice of this water, and one slice of this water will be in the shape of a rectangle. And it'll be an extremely thin rectangle of water. So it'll be almost kind of like a CD case of water. So the volume for this rectangular prism is going to be length times width times height. Well, let's see. So if I make h equals 0 at the top and increase downwards, what's the height of this going to be? What's the height of this really thin CD case? dh, right? Okay. Now the length and the width, that's going, well, those are first of all going to be the same, because it's a square base. Okay, so we have the length squared and then dh, but now we need to come up with a formula for the length in terms of the h right here. Because as we move further up the pyramid, this is getting shorter, and as we move farther down the pyramid, it's getting longer. So how are we going to do this? We're going to use similar triangles. That's definitely what I recommend doing if you ever have a pyramid shaped thing. So if we draw the side view right here, we have a height of 3 and a base of 1. Now let's say our rectangular, or sorry, our CD case slice is right here. There's the water. We want to get some relationship between how far we are from the top and how wide this is going to be, which I'm going to call this L, I guess, because I called it L there. All right. So now let's see here. How do I come up with a relationship between the two? Well, it seems like the vertical dimension is 3 times as big as the horizontal dimension. And that ratio should also work for this similar triangle, which is kind of wedged in here, h over L. So what does that mean? L is going to be h over 3, like this. So I'm going to take that and I'm going to substitute it up here. So I have h squared over 9 dh is going to be my volume for one slice of the water right here. And as always, once we get a nice formula for the slice, oh wait, no, we're not done. I'm sorry. We're not doing the volume of this thing. I mean, this is the volume of the slice, but we need to do the amount of work. Sorry about that. The work on one slice will be the force times the distance. The force we're fighting against is gravity. The distance we're traveling is h right here. And then what's the mass? Well, the mass is going to be the density times the volume, right? So mass turns into rho v. And now we just figured out what v is. So we did the hard work in advance. So we have rho h squared over 9 gh. And then I'm going to put this dh at the end. There we go. So now we know the amount of work for one slice. Where did the W go? You mean the W right here? Well, it's a square base, so the length is the same as the width. So it just turned into another L. That was what's going on up there. All right, so now we know the work it's going to take for one slice. Now let's go ahead and integrate it. Although I think I said in the problem that rho and g can be 1, so I'm just going to get rid of those. So the work here is going to be the integral of h squared times h, which will be h cubed, divided by 9. Okay, now here's the perennial question that we have with these problems. What are the bounds of the integral going to be? Where is the physical object that we're interacting with in this problem in terms of h? It's going to be 2 to 3. That's right. Because the water doesn't start until we're 2 down from the top, and then the water continues until we reach the bottom of the pyramid, which is 3 from the top. So this is going to be our integral right here. And now we're back in polynomial calc 1 land, so I will leave you guys this integral to do. We'll just use the power rule, make this be h to the 4th over 4, and then divide by 4, and then plug some numbers in. So that's how we would do, that's how we would finish off this, this pyramid one here. Now make sure you understand the bounds here, and make sure you understand why it's 2 to 3 and not maybe like 0 to 1 or 0 to 3. How to get rid of the rho g? In the problem I said rho is g is 1. Every problem will either say that or it'll say just leave your answer in terms of rho and g. All right, great. So we did this one. So now I promise that the live audience can have a question. Does anyone have a question here that they would like to ask? Yes. Homework 8, number 6. Let's take a look at that. And then we'll do the infamous homework 7, number 7, which seem to be pretty popular. All right. Let's move this up a bit. All right. So let's see here. Suppose a shape is created by revolving the region between y equals x squared, x is 0, and y equals 1 around the y-axis. This is homework 8, number 6. All right. So then what do we need to do here? If the shape is completely full of water, how much work will it take to pump all of the water over the top? Okay, as always, let's draw a picture representing this here. All right, let's see here. So here is our XY axes. That. Let's see, we have y equals x squared. We have x equals 0, so that's right here. And then we have y equals 1. That's maybe like this. So the region in between all of that is going to be this region right here. And what we're doing is we're spinning this around the y-axis. So we're making some kind of like a circular bowl that kind of looks like this. We're making a circular bowl right here, and supposedly the whole thing is filled with water. So we want to pump all of this water out over the top. Okay, now remember, this is a circular bowl, right? Because we spun this in a circle. So that means that if we look at one little slice of water right here, it's going to be circular. So it kind of looks like a flat coin shape right here. All right, so let's figure out the amount of work on one slice. Well, work is force times distance. The force we're fighting against is gravity right here. This is one of the rare problems where I'm not going to make HV0 up here and go down because we actually already have variables in this problem. I'm going to have the distance be in terms of y. Now, what would the distance be in terms of y? How would I write that down? Does anyone see what the distance to the top would be in terms of y? Well, it's not 1 for all of them, although there is a 1 in the formula. It's a 1. Oh, yeah, that's technically true. I was looking for 1 minus y. So whatever our y value is, like let's say we're 3/4 of the way up, we do 1 minus that, and then we have 1/4. That's how much we have left to go. So the difference between 1 and how far up we already are with y is going to be our distance here. Now you could absolutely write this as x squared because y is equal to x squared. So that's totally okay here. All right. Yeah, how does this work? Let me explain this again. So we're at a distance 1. We want to get up to here, right? So let's say we're at a y equals, say, 1/3. How much further would we have to go up? It would be 2/3, which is 1 minus y. If I'm 1/4 of the way up, how much further up do I need to go? It's going to be 3/4. So it's 1 minus whatever my y value is. If my y value is 1, I don't need to travel any more distance to the top. It's going to be 0. So 1 minus y is going to be my distance. And then y, another name for my y value here, is going to be x squared, since the edges of this cylinder are touching the curve y equals x squared. All right. So let's see here. Now the mass, rho v, mass is going to be the density times the volume. And then the volume here, well, we need to figure out the volume of one of these slices, right? So each of these slices is going to be a cylinder. It's going to be pi r squared and then dy, or a tiny little height in the y direction. So this is what's happening with v here. Okay. Now let's see here. What's the radius of my cylinder going to be? And remember, the distance for my cylinder is going to be from my axis all the way to my curve. So I just want the radius. I want this distance right here. I don't want the diameter. I just want the radius. What's that going to be? It's going to be x. Remember, whenever you want to measure a horizontal distance from your axis to your curve, you're going to use x for that. Yeah, what's up? Well, this d is how far we're moving the object, right? If I just had that be, oh, sorry, let me repeat the question for the online people. Why can't I just have the distance be y, kind of like we normally do with h? Well, the problem with that is, let's say my y value is 0. How far will I need to move the object? If I'm down here at y equals 0, I need to move it all the way up to the surface at y equals 1. So my distance would be 1, but that wouldn't match my y value, which is going to be 0. So doing just y doesn't work because it doesn't give the right distance that we need to move. So it's really going to be 1 minus y. We already move up a distance y, and then the difference between those is going to be how far we need to move, which is 1 minus y. Why would it not be pi r squared over 2? We're doing the volume of a cylinder here, which is pi r squared times the height, which is dy. All right, so like I was saying earlier, the horizontal distance from your axis to your curve is going to be x. Actually, I'm going to write this as 1 minus y. It was better that way. Why was it better as 1 minus y rather than x squared? Because we have a dy. That's right. We want to integrate stuff with respect to y right here. So now the only bad point that we have with that, I mean, rho, pi, g are constants. This has y's. The only thing that's not a y right now is this x squared. So what we're going to do is we're going to turn this x squared into y. And that's really easy because y is x squared. So we have rho pi y g 1 minus y dy right here. And this is going to be the work on one slice. Why is it dy and not dx? Because our very thin cylinders are very thin in the y direction. So whatever direction we're very thin in, it's going to be d whatever variable that is. How did we get the volume as pi r squared? Well, technically, this is a really thin cylinder with a very tiny height. So the volume of this very thin cylinder is pi r squared h, or pi r squared dy. And our height is dy. So then we just needed to do pi r squared, but the radius is just going to be whatever the x value is. All right, and then we're finally ready to finish this off now that we have this. The total amount of work will be the integral of all the stuff. So we have rho pi g, all of our parade of constants. And then we have y times 1 minus y. And then this integral will go from what to what? 0 to 1. That's right. The lowest y value we have is 0, and the highest y value we have is 1. We make it in terms of y because it was rotated around the y-axis. We made it in terms of y because that's the direction we had a very thin slice in. That's why we did this with respect to y, because we kind of took a very thin slice. And yeah, I guess loosely it comes from rotating it because we made a circular shape by rotating it around the axis y. So yeah, I guess that's true. What happened to the x squared? Y is equal to x squared. So I just rewrote this x squared as a y right here. All right, and then now once again, we've arrived in friendlier waters, in Calc 1 waters. And so I'll let you guys do the integral of y times 1 minus y right here. All right. Are there any other questions about this one? I really want to go over this example. This is a really important example to understand the physics stuff. So I'm going to briefly summarize this again here. I think that's going to be time well spent. We want to take this slice, this circular slice, and we want to figure out how much work is going to be done on it. So work is force times distance. The force we're fighting against is mg, or gravity, right here. Now the distance we're going to go is going to be 1 minus y. And let's look at a few examples why that is. So let's say y is 0. Let's say we're down here. How far do we need to move to get to the top? We're going to have to move a distance of 1. Let's say our y is like 1/4. So we're 1/4 here. How much further do we need to go to get up to the top? Well, we need to go 3/4. All right, let's say we're 1/2 of the way up. How much further do we need to go? Well, we need to go 1/2, and so on. And it seems like the commonality between all of these is that the sum of them, the distance we started up versus the distance we need to go, is going to be 1. So then I subtract this over and I have d is 1 minus y. Yeah. Well, that's what the problem's asking. So we're pumping water over the top here. So we're trying to physically move the water up to the top here. How do we know the water level is at 1? Because that's where our shape ends. They said the shape ends at y equals 1, and the shape was completely full of water right here. All right. So we have this. So we have d is 1 minus y, and we put that in there. It's technically 1 minus x squared, but I guess we really didn't need to do that. Reason being is that we want to have dy right here, because that's going to come from our volume. So mg, m is density times volume right here. All right, so we have m is density times volume. That's a fact from science. And then we have v is going to be the volume of our disk right here. So the volume of this, the coin-shaped disk right here, is the area of a circle, pi r squared, times the height, which is very thin, so we're going to have dy. So this is my volume here. Now, what's the radius of this? Well, remember, the radius is the distance from this axis to the curve, and that distance is going to be x. Anytime you want to do a horizontal distance from the axis to the curve right here, you want to use x for that. And then finally, we have x squared, and since it's touching the curve y equals x squared, well, we could replace that with a y. We get all of our all of our constants and all of our y's right here for one slice, and then we put it into an integral right here. All right. So if we're revolving around anything, we're going to make a circular shape, right? That's what revolve means. We're spinning around in a circle around something. So that's why we had a circular shape in this case. Even if it were around the x-axis, we still would have had cylinders. The only difference is they would have been cylinders like this, so we would have done dx for that instead. All right, I just really wanted to go over that one exhaustively because this is a really excellent example of the kind of physics problems that we have here. Now notice that we didn't use the shell or washer method for this, even though it seemed like a volume of revolution one. We kind of just needed to know what the shape was, and then we just moved into the physics zone. We weren't finding the volume of anything in particular. We're not finding the volume of this whole thing, so we didn't need the shell or washer formulas for this. All right. So we have that one. Now we want to go to homework 7, number 7 here. So let me pull that up. And the last few minutes, we can try to go over that. Let's see. All right. I think this is going to be the last one we're going to have time for here, unfortunately. All right. So find the volume of the solid. So this is 7.7, homework 7, number 7. Find the volume, V, of the solid generated by revolving the region between let's see, x squared plus y cubed equals 4, x is 0, x is 2, and y is 0. And we're spinning it around the y-axis right here. Okay, as always, for any of these problems, we're going to draw a picture. Oh, yeah, sorry for the audience members here. All right, so we have x equals 0. That's right here. We have x equals 2. That's right here. We have y equals 0. That's right here. And then we have this guy. We have y cubed plus x squared is 4. Now I'm going to solve this, since x's and y's are mixed together here, I'm just going to solve this for y. So I have y cubed is 4 minus x squared. And then y is the cubed root of 4 minus x squared. All right, so let's see here. Now, this function's a little bit strange, right? Like you may not know what the graph of this looks like on the top of your head, but we could plug in a few values to kind of see what it's going to do in general. And we know that this thing is going to be between x's 0 and 2. So we really only care about values in there. So if I plug in x equals 0, I get the cube root of 4, which is like 1 point something. So why don't we say that's right here? Then as our x gets bigger, our input gets smaller and smaller and smaller until we get to x equals 2. And then what is this function going to be? It's going to be 0, right? So once we get down to 2, we're going to hit 0. And I'm not exactly sure which way this curve bends or whatever, but it's going to be something like this. And I know it's going to be positive the whole time, most notably. Now, what we're going to do is we're going to spin this around the y-axis. Looks like a what? Yeah, that's right. Yeah, it looks like an upside down pole. All right. So we're going to spin around here. Now let's put into practice what I was saying earlier. We have y as a function of x, and we're spinning around the y-axis. So which method should we use for this one? We should use the shell method for this one. That's right. Because we have y as a function of x, and we're spinning around the y-axis. When the variables are opposed, we use the shell method. So the shell method says that the volume will be 2 pi times the integral, and we'll talk about the bounds in a second. We have an x in there by default, and then we have our higher curve, which is the cube root of 4 minus x squared, minus our lower curve. Now this one goes all the way down to the axis. It goes down to y equals 0. So technically that's just minus 0, but you could have just omitted that in the beginning right here. If we solve in terms of x, can we do the washer? Yeah, so if you decided to do this the other way around where you solve for x, yeah, you could have done the washer method instead. That's right. All right, now we need to talk about the bounds. The lowest x value that this has is 0. This is where the thing starts. And let's see, the highest x value we have is 2. So that's going to be our integral, going to be here. Where did the x outside x come from? That comes from the formula for the shell method. The shell method has an x in there by default. Okay, now this integral isn't quite as easy as the other ones we've done today. How would you guys recommend that we do this integral? We're going to do u substitution. And what would we make our u equal to for this? 4 minus x squared. I see some people saying trig sub. You could technically try trig sub with this, but the Pythagorean identity is not going to work well with this cube root. That's going to be kind of awkward. So I would really go with u sub for this one. And we have du will be negative 2x dx. Oh, that's almost what we have. We have a 2 and an x here, but no negative. So I'll move that over here. Now we do have a 2x dx. So we can substitute this in here. All right. So we have negative the integral, and then we have our constant pi. That didn't change. And we have the cube root of u du. All right, now we have two options at this point. We could just write x is 0 and x is 2 for our bounds, reminding ourselves that those bounds were the old ones. Or we could get new bounds by substituting in these values into my u equation. I'm going to do the new bound way because I think people are less comfortable with that. So I want to give you guys more exposure to that, because oftentimes this is the superior way of doing these problems. So I'm going to take 0 and I'm going to put it in for my x, right? And it's going to give me my new u bound. What is my new u bound going to be for the bottom? It's going to be 4. And remember, the way I got that is I took my old bottom bound, put it in my u formula, and I had 4 minus 0 is 4. That gave me 4 down there. Now I'm going to get the top bound. I'm going to take 2. I'm going to put it into here. 4 minus 2 squared is 0. So my new top bound is 0 right here. Now we're going from 4 to 0. That's awkward. That's not in the correct order. Now remember, we can fix that by getting rid of the negative sign. So this is now the integral from 0 to 4 of the cube root of u du right here. And now we're back in Calc 1 land, because this is u to the 1/3. So I raise this to be u to the 4/3, and I divide by 4/3, which is multiplying by 3/4. Yeah, this is not going to be a nice number. So I'm going to put 4 into here. So I have pi times 3 times 4 to the 4/3 over 4. And then I put 0 in there, that's going to be 0. And I could simplify this mildly into 3 pi times the cube root of 4. And there we go. There's going to be that. What happened to the negative sign on the pi? Well, this was going from 4 to 0, but I want it to go the correct order, so I can use a negative sign to flip the order of my integral. So that's where that negative sign went. All right, and notice that the advantage of this is once I flip to u's and I change my bounds, I never saw x again. I never wrote another x on the page. I didn't have to go and back substitute and do that or anything. I could just plug in the new numbers and I'm good to go. All right, let's see here. Well, looks like we're out of time, but remember, next time it's going to kind of just be office hours, so you guys can feel free to come and ask more questions if you guys like here. All right, feel free to email me if you have any other questions as well, and I will see you guys on Friday. So happy studying.